In mid-February 1943, at Sidi Bouzid, Mamoun Ahmed, events unfolded. In the middle of February 1943, at Sidi Bouzid in Tunisia, a scene took place. The seized M4A1 Sherman tank halted in the desert sands, its American star still partially visible under the rapidly applied German cross. Officers of Heavy Panzer Battalion 501 assembled around this captured vehicle, their notebooks already out. This lone intact and functional American tank, taken during the Battle of Sidboid, would set off a confidence crisis for German engineers that would influence their armored vehicle development for the remainder of the conflict. The calculations of armored combat were about to be altered fundamentally, not through improved weapons or thicker protection, but due to something the Germans had not previously valued: mechanical reliability that simply would not fail. The tank displayed the designation War Daddy 2 on its hull. Serial number USA 3,067,641. It was manufactured by Lima Locomotive Works and assigned to Company G, 1st Armored Regiment, 1st Armored Division. Troops from a German reconnaissance group drove this Sherman for 350 kilometers over North African ground to the port of Sfax, an expedition that took 4.5 days. Each kilometer showed something new that challenged German beliefs about American manufacturing abilities. The engine remained cool. The transmission operated without issues. The final drive components performed reliably throughout. Experienced in ongoing mechanical breakdowns even on limited moves, German tank crews looked on with increasing apprehension as this American tank ran faultlessly through land and environments that would have incapacitated their own machines. Upon arrival at the port, War Daddy 2 was shipped aboard a freighter headed for Germany. Specific orders from the Army Weapons Department made it clear. This tank was to arrive at the testing center in Kummersdorf undamaged and running. German intelligence services had received incomplete intelligence regarding American tank assembly. However, inspecting the tangible vehicle gave reality to those production figures far beyond what data alone could convey. The Sherman was an example of mass production on a level Germany was unable to equal. It was constructed using engineering methods for automotive durability that German industry had not achieved. As the vessel traveled north over the Mediterranean, Wehrmacht engineers set up testing regimens to reveal facts they had hesitated to acknowledge about both their shortcomings and American strengths. In the spring of 1943 at the Kummersdorf Proving Ground in Brandenburg, Germany, War Daddy 2 was unloaded from its transport railcar, displaying the marking for Zugfahrts 259 along with the German license plate WHO 58941. Test engineers had already painted armor thickness values and slope indicators all over the tank's surfaces, annotating it thoroughly for their in-depth evaluation initiative. Situated 25 kilometers south of Berlin, the German military proving ground at Kummersdorf functioned as the chief test site for both German vehicles and captured Allied hardware. At this facility, meticulous engineers assessed, examined, and scrutinized everything from track slack to gearbox efficiency, recording every discovery in expansive technical documentation. The Sherman now faced the most thorough mechanical assessment German technical experts were capable of conducting. Initially, German test personnel began their inspections alongside groups of experts from several technical divisions. They photographed each part from a multitude of perspectives, checked all clearances with accurate tools, and took note of manufacturing practices that appeared almost surprisingly uncomplicated compared to German standards. Powertrain experts immediately focused their attention on the Sherman's transmission system. Unlike German tanks, which relied on straight-cut gears demanding exact tolerances and constant upkeep, the Sherman employed herringbone gears that spread force across several teeth at once. This method, long used in American auto production since the 1930s, gave significant longevity with only moderate precision needs. German design staff had previously deemed herringbone gears impractical to manufacture in large quantities given their production resources and the skills of their workforce. Meanwhile, the Americans were producing such gears by the thousands. Testing commenced with elementary automotive exercises intended to challenge each mechanical assembly under regulated settings. Engineers put War Daddy 2 through obstacle routes engineered to mimic battlefield situations, charting fuel usage, tracking engine heating, and logging transmission response to fluctuating load and ground conditions. Following every test run, parts were dismantled to inspect wear marks, investigating for evidence of strain, poor lubrication, or design flaws. Outcomes disputed all conventional German armored doctrines regarding the perceived compromise between capability and dependability. The Sherman met requirements in all evaluated fields and excelled in the one criterion where German vehicles consistently struggled: the ability to operate for extended periods without requiring repairs. The inspection of the powertrain outlined divergent design philosophies underlying American and German tank manufacture. Sherman's gearbox featured 5 forward gears and a reverse, with synchronizers on gears 2 to 5, which removed the necessity of double clutching under normal use. As a result, driving the Sherman was almost as manageable as operating a standard automobile, and driver training did not need to be as specialized. German crews, on the other hand, invested significant effort mastering intricate double clutching and precise throttle use to prevent their transmissions from sustaining harm. The Sherman's approach assumed average soldiers possessing rudimentary mechanical skills would handle these tanks, whereas German construction relied on the availability of expert technicians. The Continental R975 radial engine in this specific Sherman proved exceptionally adaptable to a wide range of operational environments. Technicians observed that this engine provided reliable performance in temperature extremes that typically resulted in German engines overheating or suffering power loss. The straightforward cooling setup still managed to achieve impressive effectiveness. The desert sand was no match for the air filtration, which operated without the regular blockages that German tanks in North Africa frequently experienced. Each component showcased an engineering mindset that valued practical reliability more highly than purely theoretical improvements. June 6 and 7, 1943. Hille-Leine Artillery Range. Reichsminister Albert Scharr personally attended a significant weapons conference, which brought together major figures from the arms sector and senior Wehrmacht officers. The schedule included hill climbing tests that pitted German armor against captured Allied vehicles. War Daddy 2 was displayed alongside the newest German models, including a Panther ACEF Diem just off the assembly line, and a Ferdinand tank destroyer that stood as Germany's peak armored vehicle engineering. Scharr, who oversaw German armaments manufacturing and reported directly to Hitler regarding outcomes, needed insight into both the capabilities of American industry and how German armored vehicles performed compared to their adversaries' machines. This demonstration procured results that neither Scharr nor the German tank engineers were eager to confront. The Sherman advanced up the test grade with no trouble. Its 5-speed manual gearbox, with 2nd to 5th fully synchronized, shifted gears seamlessly throughout. The engine kept up steady power all through the climb. The driver maneuvered the tank confidently, illustrating the Sherman's reputation for simplicity in operation. The Panther, powered by its more robust 700 horsepower Maybach HL230, managed to stay with the Sherman in the trial, but not without appreciable added effort and difficulty. At 65 tons and equipped with an advanced electric transmission, the Ferdinand's considerable mass led to a stall midway on the hill. Speer observed as tow teams scrambled to restart it, a humiliating incident unfolding in full view of dozens of high-ranking officials and industry executives. Reflecting later in his memoirs, Speer recalled the Sherman's attributes he saw during his Italian inspection trip in October 1944. He mentioned that field assessments of the Sherman's off-road agility were overwhelmingly positive, noting the tank's capacity to climb slopes that German tank specialists had considered inaccessible. He credited this to the Sherman's engine, which offered an especially favorable power-to-weight ratio, giving it cross-country movement on flat surfaces that was markedly superior to German tanks. The 26th Panzer Division had actually highlighted this particular advantage. These findings from the armaments minister influenced discussion within Wehrmacht leadership circles. Das Reich newspaper published an official analysis on June 27, 1943. The story designated the Sherman one of the exceptional achievements of North American research and called it an especially commendable creation of the North American steel industry. According to the article, the initial standout qualities were its serial manufacturing methods and the fulfillment of the almost bold demands of the North American automotive sector. The piece referenced the gyro-stabilized gun as the premier example of its kind globally, recognizing American ingenuity in this technology. Though these comments were cautiously crafted to serve propaganda aims and not suggest defeatism, they masked the private concern rippling through German engineering circles. American tanks proved not merely adequate, they were basically better suited to the demands of prolonged deployment. Meanwhile at Kummersdorf, a thorough testing regime went on through summer into fall 1943. Technicians logged the operational reach of the Sherman with rigorous, long-endurance testing, pushing the tank's operational boundaries. They recorded operational distances greater than 2,000 kilometers before major servicing was necessary, roughly quadruple the range early Panther models managed under field service. Gearbox efficiencies were measured, and these surpassed those of any German armored vehicle, with power losses through the transmission notably less than what comparable German machinery exhibited. Engineers analyzed the synchronized manual transmission, which allowed for straightforward and fluid shifting, eliminating the need for double clutching or careful rev matching essential for German gear systems. Final drive units were another area that appended prevailing German engineering views. On Panther tanks, the final drive system used inherited components from the Tiger, a setup that struggled under the stresses of a 45-ton chassis. These designs employed straight-cut gears in housings that failed to withstand the loads of such weight. German maintenance personnel in North Africa and the Eastern Front cited final drive malfunctions that led to Panthers being deserted after short movements, sometimes as little as 100 kilometers. In contrast, the Sherman's final drives built using the herringbone gear method like their transmissions seldom malfunctioned, even during prolonged combat that would have destroyed German units. Even decades on, restoration work often found Sherman final drives that didn't need repairs after years of storage, highlighting how much their design exceeded immediate wartime requirements. By the close of 1943, Kummersdorf's continuing tests had resulted in detailed internal reviews issued to Wehrmacht technical departments. These confidential memos for top Wehrmacht officers and weapons ministry figures laid out a stark contrast between forces. The Sherman exemplified the practicality and maturity of American automotive engineering, something Germany was fundamentally lacking in, for all its advanced theoretical skills. Mass production in the U.S. produced tolerance levels that German specialists might have deemed imprecise, but that ultimately delivered vehicles with superior operational dependability. Swappable parts meant that field repairs could be handled with little training and basic tools. In contrast, German vehicles often demanded factory-standard precision and special tools on-site for repairs. The overall philosophy strongly favored field operability over chasing theoretical specs that, while impressive on paper, were unattainable during the stresses of war. German internal engineering reports recorded observations concerning American industrial strengths that extended beyond mere manufacturing statistics. The field of American automotive engineering demonstrated years of civilian sector development that Germany had not achieved at a similar magnitude. Prior to the conflict, the United States experienced broad levels of car ownership, with automobiles present among everyday people from all income backgrounds. Germany's experience with civilian cars was much more restricted, as automobiles remained exclusive possessions for affluent individuals and members of the Nazi Party elite. Since 1934, the Volkswagen Initiative had promised affordable cars to German laborers but had produced under 1,000 civilian units by 1939. This major disparity in automotive industry experience directly influenced armored vehicle development approaches. The United States produced tanks that civilian-trained automotive mechanics were able to service using pre-existing expertise. Conversely, German tanks demanded specialized technical training and the ongoing skills of technicians with extensive, military-grade education. The reality of German tank dependability became unavoidable as operational reports built up through the end of 1943 and into 1944. Panther tanks had to operate within specific limits to reduce the risk of debilitating mechanical issues. Operators were given direct guidelines not to shift gears frequently, as repetitive gear changes harmed the gearbox. The third gear often failed, prompting manuals to advise its use only in the most necessary circumstances. Reversing and steering simultaneously in a Panther would damage the gearbox beyond use. Pivot turning was allowed only if resistance on both tracks was exactly balanced, sharply confining battlefield maneuverability. If debris made its way into the running mechanisms, the drive sprocket could become immobilized, leading to several laborious hours of repair work. These issues persisted even though Panthers were assembled in purpose-built facilities by highly trained personnel using the top-quality materials available within Germany. Conversely, the Sherman was developed by automotive engineers at General Motors, Chrysler, and Ford who utilized large-scale manufacturing techniques refined through long-term civilian car production. Wherever practical, standardized commercial auto parts were used in the Sherman, making use of current supply networks and industrial know-how. The tank's transaxle was supplied by companies like Ford Motor Company, Buick, and Caterpillar Tractor, all of which built units to uniform standards, resulting in fully interchangeable components which could be swapped without special modification. This level of standardization, a normal practice in the American automotive field, was mostly absent in German armored vehicle manufacturing, where each producer contributed small changes that stopped parts from being truly interchangeable.